Welcome all for this new topic which I am picking up today, and this new topic is fluorimetry. And this fluorimetry is an extended topic which falls under UV spectroscopy. And the reason being for inclusion of this topic along with the UV absorption or UV spectroscopy is because this is a complementary technique which happens post absorption phenomena. So most of them try to include this fluorimetry as a complementary topic for UV spectroscopy. So myself, Dr. Girish Hampanava, Assistant Professor, Department of Pharmaceutical Chemistry, KLE College of Pharmacy, Vidyanagar, Hubli. Would like to engage you guys with this particular topic. So in this topic, we'll be discussing a bit of introduction, some of the definitions, the theory behind this fluorescence and phosphorescence, and there are some factors that affect this fluorescence phenomena, and we have an instrumentation to be studied in detail, and some applications which we come across in pharmacy, and some conclusions, and followed by some references. So coming to the introduction of this fluorimetry. So before I go for the subsequent slides, I would like to share some of the things why we actually go for this fluorimetric technique. So a large number of chemical species, we know that they absorb the UV radiation, and the moment they absorb the UV radiations, which we studied in the previous discussions, the moment the molecules absorb the energy in the form of UV radiations or UV visible radiations, the electrons undergo excitation and they end up landing in the higher energy states. And once these electrons are landing up in the higher energy states, they tend to relieve the energy which they have taken up to travel from ground state to the excited state. I mean, from the ground state to the excitation state. They tend to release that energy. Okay, so most oftenly the molecules lose this energy as heat through some collision process with some neighboring atoms or molecules. However, most important or some of the important substances which lose this energy through collision or through heat, but still a part of this energy is emitted as a form of electromagnetic radiation. But since the energy is lost, a part of the energy is already lost in the form of heat or collision, the remaining part of energy which is emitted as the emitted radiations, these emitted radiations have lesser energy than the radiation what they had taken up for excitation process. So this emitted radiations which is because by the virtue of the returning of electrons from the excited to the ground state, these radiations have a longer wavelength than the absorbed radiations. So this process of emitting radiations is collectively known as luminescence. So I'll come to this luminescence. Luminescence is an emission of the light by a substance, and it occurs when an electron returns to the electronic ground state from an excited state and loses its excess energy as a photon. So as I mentioned, the electrons, while returning from the excited state to the ground state, they tend to dissipate the energy, whereas the part of the energy is lost as collisions or is dissipated as heat. The remaining part of the energy is dissipated as an electromagnetic radiations, and that we call it as that part of the energy which is lost, we call it as electromagnetic radiation, which is nothing but a photon or the light. This light we call it as the luminescence, and this luminescence is a light that is produced without any heat or without any application of external energy. So we call this light as light without heat, or we also call it as a cold light. So this luminescence is of three different types. The first one is fluorescence, the second one is phosphorescence, and the third one is the chemiluminescence. We are not discussing much about the chemiluminescence process, whereas we will be discussing in detail about the fluorescence and the phosphorescence. That is very important in spectroscopy. So Coming to the fluorescence, as I have mentioned, when a beam of light is incident on certain substance, they emit visible light or radiations, and this is known as fluorescence. The entire phenomena of emission of light, we call this as a fluorescence, and the substance which is showing this phenomena, we call them as the fluorescent substances. And basically, this emitted light or this fluorescent light which is emitted is of longer wavelength compared to the radiation which is used for the excitation process or the absorption process. So there's one more important thing associated with this fluorescence is that the phenomenon of this fluorescence is instantaneous, and it starts immediately after the light has been absorbed, and it stops as soon as the incident light is stopped. So it means the moment the incident radiation is put on, the fluorescence is visible, and the moment you put off the incident light, the fluorescence stops. So this is what we define fluorescence as. Coming to phosphorescence, phosphorescence is another kind of fluorescence, but somewhat different. We'll understand how different is this. When light radiation is incident on certain substances, they emit light continuously even after the incident light is cut off. So it means the same molecule which we took for understanding the fluorescence. Think of the same molecule which is absorbing the radiations or the UV radiations, and it is getting excited, and while returning it shows a sort of fluorescence. But the fluorescence is, if it is happening continuously even after putting off the incident light, we call that phenomena as phosphorescence. And this phosphorescence is also called as a delayed fluorescence. Why we call it as delayed fluorescence? It is because even if we put off the incident light, the fluorescence keep on happening, and we call that as a phosphorescence. And the substances which shows this kind of phosphorescence, we call them as the phosphorescent substances. So the materials, coming back to the previous slide, the materials or the molecules which exhibit fluorescence, they generally re-emit the excess of radiation within 10 to the power 6, 10 to the power minus 6 or 10 to the power minus 4 second of absorption. I mean to say, the re-emission happens within this fraction of time, that is 10 to the power minus 6 to 10 to the power minus 4 of a second. So it is so fast, the moment the light is put on, within 10 to the power minus 6 seconds the fluorescence begins, and if you put off, it stops, or the fluorescence stops immediately. Whereas on the other hand, the phosphorescence, as I said, it is a sort of delayed fluorescence. The re-emission or the emission of the or the re-emission of the radiation, it happens from 10 to the power minus 4 to 20 seconds or even longer. So it is sort of a delayed process of fluorescence. That's why we call it as a phosphorescence. So these are the two different techniques we will be considering for discussion in this particular fluorimetry title. So coming to the theory part, before I go to this theory part, I would like to tell about the differences what we come across this absorption and fluorescence process. We have studied the absorption process in the previous discussion, that is UV spectroscopy, whereas the fluorescence is the one which we'll be discussing in this particular topic. So what is the advantage of measuring the fluorescence rather than absorption? We have some advantages why we measure fluorescence instead of absorption, because the absorption methods have some of their own limitations, whereas the fluorescence or the molecular fluorescence do not have such limitations. So we have certain wavelength choices in fluorescence phenomena, whereas in absorption process we do not have such wavelength selection option. So in fluorescence we have two different wavelengths where we are working at. We work at excitation wavelength and we work at emission wavelength, whereas that is not possible in absorption. in absorption process, we rather try to work only at the absorption maxima, which we call as lambda max. So if there are any interferences in absorption process, that can be avoided by going to this fluorimetric technique. How can we do that? We can simply shift to the other wavelengths where the fluorescence is still happening, whereas if you shift to the other wavelength, the absorptions may not be proportionally happening, whereas the fluorescence still happen at the other wavelengths other than the absorption maxima. So in spectrophotometric absorption procedures, serious errors may result because we are using the other wavelength other than the absorption maxima, whereas that kind of serious errors can be avoided by going to this fluorimetric technique. So that is an advantage of using fluorescence when compared to the absorption techniques. Coming to the theory, what I have just now said is a very crucial part of this particular discussion, where I have some animations later in this discussion. So this theory tells us about, or rather it helps us to understand about the process of fluorescence and the phosphorescence that is happening in this particular technique. So the molecular electronic states in which all of the electrons, we know that when all of the electrons are paired, are called as a singlet state. Okay, and in order to understand this singlet state, I have more meaningful slides hereafter, whereas this we will understand the singlet state, we will understand the triplet state, and so on and so forth, and various diamagnetic and paramagnetic properties that are involved with this singlet and the triplet state. So coming to the singlet state, in this singlet state, the spin of two electrons are paired and are diamagnetic. Diamagnetic means they do not exhibit any magnetic field, because the spin of these two electrons are paired in nature. The magnetic field generated by each is nullified because the spin is paired, and ultimately there is no magnetic field that is visible out of this singlet state. So the diamagnetic molecules, if this spin is a paired spin, then the molecule as a whole is a diamagnetic, rather they do not exhibit any of the magnetic field by themselves. If they are not exhibiting any magnetic field by themselves, they are not attracted, or neither attracted nor repelled by the external magnetic field. So we call them as a diamagnetic. That happens in the singlet state where the spin of two electrons are paired. So most of the molecules in the ground state, we know that they are paired. Okay, and since they are paired, they are diamagnetic in nature, and since they are diamagnetic in nature, they do not, or they are not influenced by any external magnetic field. When such molecule which is having which is in a singlet state and having a paired electrons, when such molecules absorb the UV radiation, one of the paired or one or more of the paired electrons get excited, and this excitation leads to the shifting of that particular one or more of the paired electron, that is shifted to the excited singlet state, or maybe to the excited triplet state. I will show all of this theoretical thing by animation in the subsequent slide. So when they absorb the UV radiations, and let me tell you, not all the molecules show up fluorescence or phosphorescence. Only some molecules with some electronic parameters, or only some molecules which absorb the UV visible radiation, will tend to show this fluorescence or phosphorescence. So a molecule should be excited by this UV visible radiation, only then they are showing fluorescence. So when there is a singlet state, such kind of electrons, they take up the energy and they end up in an excited state, excited singlet state, or an excited triplet state. We have two such excited states. One is singlet excited state and the other one is triplet excited states. So molecules in the triplet state have unpaired electrons and are paramagnetic. So these unpaired electrons have the same spin, and Since because of the same spin, the magnetic moment gets added up, and that's why they behave as a tiny magnets. So they are called as paramagnetic, and because they are paramagnetic, they behave as a tiny magnets. Since they behave as a tiny magnets, they tend to be either repelled or attracted by external magnetic field. So the triplet state, in the triplet states, they tend to behave as a paramagnetic, and in the singlet state, the electrons tend to behave as a diamagnetic. That is, they don't show themselves as a tiny magnets, and because of they do not have any magnetic nature, they are neither attracted nor repelled by the external magnetic field. So these are the singlet states and the triplet state representation. As I said, in the ground state, the electrons are paired. They are always paired. And in the excited state, or in the excited singlet state, the spin is still paired and there is no magnetic moment, and that's why they are, as I mentioned, they are diamagnetic in nature. Whereas in the triplet state, in this particular state, there is the spin, they are unpaired, and the net magnetic field is observed here in this particular triplet state. So the singlet excited state and the triplet state, they are both the excited states, whereas the ground singlet state is the ground state. So when the electrons absorb the UV radiations of some proper frequency, one or more of these paired electrons, they tend to generally the pi electrons, they tend to take up the energy and they get raised to an excited singlet state, or they get excited followed by the triplet state. So this both states, as I mentioned, they are the excited states, and in the excited state, the spin of the electrons do not change, and if the net spin is still 0, then we call it as an excited singlet state. And if the spin is changing, and if it is changing, then we call it as the triplet state. And these are the two possibilities which may happen. And the third possibility is the electrons may get excited and they end up landing in the excited singlet state, and they may lose energy. Okay, and once the electron is in the either excited singlet state or in the triplet state, they are born to or they are supposed to lose their excess energy. Okay, that is what we understand as fluorescence and phosphorescence. We'll come to that discussion in the subsequent slides. So we'll speak about this electrons which are in the molecular orbital. They are paired, as I mentioned, in the ground state, and according to Pauli's exclusion principle. This is according to the Pauli's exclusion principle. So when an electron absorbs enough energy, it is usually the pi electrons, as I mentioned, they will be excited to the higher energy state, but will keep up the orientation of its spin. The molecular electronic state in which the electrons are paired, we call it as a singlet state transition. The molecular electronic state in which the two electrons are unpaired, which I have just now mentioned, is called as a triplet state. And this triplet state is achieved when an electron is transferred from a singlet energy level into a triplet energy level by a process called as intersystem crossing. I will come to this definition and we'll try to understand what is the intersystem crossing in the subsequent slide. And this intersystem crossing is accompanied by a flip in the spin. So that was about the understanding of the singlet state and the excited singlet state and the triplet state. So coming to the phosphorescence phenomena, as I mentioned, there is a difference between the fluorescence and the phosphorescence, and the light emitting at once the source starts and stops. When the source stops, we call it as fluorescence. And if the light is still emitting, okay, let me animate this. This is a source of radiation, which is nothing but our UV visible radiations. When we switch on this UV visible radiation, consider this as our sample cells, which are containing a sample which are showing fluorescence or phosphorescence. And when we on this radiation source, the sample tends to show the absorption. and when we put off this radiation source, the sample will stop showing the fluorescence. So the moment we on this source, the fluorescence starts. The moment we put off this fluorescence stops. On putting on the source, the fluorescence will on, and on putting off this radiation source, the fluorescence will stop. So it is the fluorescence is an instantaneous process. The moment we switch on, the fluorescence starts. The moment we switch off this light, the fluorescence will stop. Whereas the phosphorescence, as I said, it is a delayed fluorescence phenomena. When I put on the source of radiation, the phosphorescence starts. When I put off this source, I have now put off the source, but still there is a fluorescence happening. So this we call it as a delayed fluorescence or the phosphorescence. That is the difference between the fluorescence and the phosphorescence. So now, understanding the spin of this singlet and the triplet state, which we have just now discussed, I am trying to represent, because I said since they are paired and since they are unpaired, the net spin sometimes is 0 in the singlet state, or it is 0 always in the singlet state, because there is an opposite spin. Whereas in the triplet state, they tend to behave as the magnetic as a tiny magnet, because of the pair, the unpaired property, and because of this unpaired property, the magnetic moment gets added up, and there is a net magnetic field observed. That's why these triplet state molecules, they are paramagnetic, whereas the singlet state molecules, they are diamagnetic in nature. Okay, so this is an electron which is having a particular direction, and this is the spin which is happening from left to right, and this is another electron, or rather I can say these are the pair of electrons which are having a different spin, and these spin are paired in nature. Once they are paired, there is no net magnetic moment that is visible, because the magnetic moment of one gets nullified with the other, and that's why there is no magnetic moment visible. In the triplet state, if you can see, the orientation of the two electrons is in the same direction, and the spin is also in the same direction. Because of this same direction, orientation, and the spin, there is a combined magnetic moment. The magnetic moment of one electron gets added up to the other, so there is a net magnetic moment that is observed. That is because of the same spin of these two particular electrons. So this is what we call as a singlet state, and this is what we call as a triplet state. So we should be very careful in understanding when I tell what we mean by a singlet state. Down the lane, we will be taking this terms as a singlet state and the triplet state, and excited singlet state and the triplet state, which is an excited state already. So the orientation and the spin should be kept in mind before we understand the discussion in very detail. Coming to, as I mentioned, when a molecule is subjected for UV visible radiations, in this particular case, the molecules will take up the energy. Not all the molecules, as I mentioned, only certain natured molecules which have pi electrons will take up this energy, and they get excited. Once they get excited, as I have mentioned, this excited states won't stay for long. Rather, they tend to relieve that excitation energy, and that excitation energy may be in several of these forms, either in the form of fluorescence, phosphorescence, delayed fluorescence, internal conversion, external intersystem crossing, intramolecular charge transfer, conformational change, electronic transfer, energy transfer. The energy may be lost in any of these ways. So basically, there are two general ways in which the energy is lost. We categorize them as radiative and non-radiative processes. And in the radiative process, the fluorescence and phosphorescence are considered, whereas in the non-radiative processes, they are the vibrational relaxation, intersystem crossing, and the internal conversion. So the energy is still lost, but there is no any emission of electromagnetic radiation in this set of processes. So these are the ways in which the excited molecule will tend to relieve the energy, either in the radiative or in the non-radiative forms. So we'll be considering the discussion of this fluorescence and phosphorescence, which are the radiative processes. And during this discussion, we will also understand what we mean by vibrational relaxation, what we mean by intersystem crossing, what we mean by internal conversion. So let me take up the fluorescence phenomena. As I have mentioned, the electrons in the singlet state, they are paired and they do not have any, they are diamagnetic in nature and they are paired. So when these electrons, one or both of these electrons, when they take up the electromagnetic radiation in the form of visible radiation, when they take up the energy, one or two of these electrons will tend to take up the energy and they try to shift to the higher energy levels. So this S0 is the ground state where these electrons are always present, and the moment they take up the energy in the form of electromagnetic radiation, which is visible radiation of lambda 1, they take up the energy and they tend to jump to the higher excited states. So S1, S2 and S3 are the excited energy levels. So this particular electron has taken up the energy and it has jumped to the excited state. So depending on the type of the energy it is taking up, or depending on the wavelength of the energy that is being made to fall on these electrons, the electrons may either go to S1, S2 or S3. And as we know, these excited states will have several vibrational energy levels within them. So when I say this electron is losing energy, it may lose energy in two different forms or in three different forms. So the first form is the fluorescence, wherein which the electron will tend to jump from this excited singlet state to the ground state, and during this process it will relieve the energy in the form of fluorescence that we'll be discussing in this particular slide. There is one more possibility of this electron losing energy. We call it as a vibrational relaxation process, wherein or we also call it as a collisional deactivation, wherein which the excited singlet state the electron in the excited singlet state is brought back to the ground state by collisional deactivation without emitting any radiations. That is a non-radiative process wherein which this electron simply relieves the energy without emitting any electromagnetic radiation. And the third possibility, as I said, this electron, since it is paired now, it may go unpairing and it may go to the another state, which we call it as a triplet state, where in which this triplet state is a metastable triplet state, where in which the electron, this particular electron will change its spin momentarily and will stay for long here in the triplet state, then come back to the ground state. And this is a sort of the delayed process, what we call as a delayed fluorescence or phosphorescence. I'll be discussing with the help of these animations both this fluorescence and phosphorescence in very detail. So this electron has coming back to the fluorescence, this electron has taken up the energy and it has gone to the excited state, and this electron, because of vibrational relaxation process, will lose the energy because it may collide with some intermolecules or the atoms or the neighboring atoms. It may collide, and because of the collision, this electron will lose up the energy, and we call that as internal conversion, and it is a non-radiative transition. And because of this internal conversion, the electron will end up in the lowest excited state. Okay, so this losing of the energy may be either because of this intermolecular collisions, or it may lose up the energy by the internal conversions. And this internal conversion, as I mentioned, is a non-radiative process, and this electron will come back to the lowest excited state. Once it has come back to the lowest excited state by internal conversion and by intermolecular collisions, it will tend to lose up the energy in the form of fluorescence. So it will come back to the singlet state by losing the energy as in the form of fluorescence. And usually the wavelength lambda 2, when compared to the lambda 1, this lambda 2 is higher compared to lambda 1. And since this fluorescence is not happening at the shorter wavelength, rather it is happening at the longer wavelength, the whole process will take 10 to the power minus 4 to 10 to the power minus 8 seconds. And lambda 2 is greater than lambda 1. I would like to animate this fluorescence phenomena, then discuss it once again. So this was the animation which I had just now shown. I will briefly take you through this animation once again. These are the electrons which are present in the singlet state. They take up the energy and they take up the appropriate energy. Not all the electrons get excited for all the electromagnetic radiations, but it is very limited scope for the electrons for a limited range of electromagnetic radiations. Let me call that as lambda 1. So when these electrons take up the energy, one or more of these electrons will take up the energy and go to the excited state. And these excited states have several energy levels, and depending on the amount of energy they take up, they go and shift to the respective excited energy levels. And in this excited energy levels, the electrons will tend to lose their energy by intermolecular collisions, and they lose a part of energy in this particular process, and that part of the energy what they lose here and thereafter the remaining energy is emitted as a fluorescence. So that is why the lambda 1 has a more energy when compared to the lambda 2, which is having lesser energy and is at the longer wavelength, because a part of the energy is lost already in the intermolecular collision process. And this an electron in the excited state will tend to lose the energy with intermolecular collision and undergoes internal conversion, which is a radiationless transition process between the energy states of the same spin state. And this internal conversion is a non-radiative transition process, wherein which the electron will hop down between these vibrational energy levels and then back to the lowest excited energy level, and then come back to the least energy excited energy level, wherein which it is now ready for jumping back to the singlet state or the ground state, singlet ground state. So during this jumping from this S1 to the singlet ground state, the electron will dissipate the remaining amount of energy, which is the lambda 2 in the form of electromagnetic radiation, which is having this particular wavelength, which falls under the fluorescence category. And this wavelength is usually longer than the one which we used for the excitation process. And this entire fluorescence process, as I said, as I mentioned, it happens within 10 to the power minus 4 to 10 to the power minus 8 seconds of this absorption process. So the moment the absorption is made or happening with this electron, the whole process of fluorescence will happen within this fraction of a second. So I have already mentioned this lambda 2 or the fluorescence wavelength is always longer when compared to the UV visible radiation. That's why the fluorescence happens at the longer wavelength and the lesser energy, whereas the lambda 1, which is the UV visible radiation, is of shorter wavelength and higher energy. This was all about the fluorescence phenomena. Coming to the phosphorescence phenomena, which is somewhat similar to the fluorescence, whereas the phosphorescence, as we know, we also call it as a delayed fluorescence phenomena. Again, we have the electrons in the ground state. We excite these electrons with UV visible radiations. Maybe two or one of these electrons take up the energy and they go for the excited state, and they from this excited state they tend to enter one more state called as a triplet state, where you can see the spin is now unpaired. I mean to say the electron orientation. I will go back with the animation. Now you can see the electrons were paired. Were paired with each other in this singlet and the excited state, but it will flip. The electron will tend to flip by this process, what we call it as intersystem crossing. The intersystem crossing is a phenomena wherein which an excited singlet state electron will enter into another state, a metastable triplet state, where the spin of the electron changes, and the now arriving state, we call it as the triplet state, which has the same spin as that of the singlet state electron. So there is a change in the spin state while the electron was traveling from the excited singlet state and entering to the metastable triplet state. There was change in the spin, and this decay from singlet excited state, or this traveling from the singlet excited state with a change in the spin, we call it as we call it as an intersystem crossing, and this journey will end up this particular electron in the state called as the triplet state. And the journey from singlet excited state to the triplet state, we call it as an intersystem crossing process. And this electron has because of the spin forbidden there is a forbidden in the spin symmetry, wherein which this electron will stay here in the triplet state for very longer time, and then get back to the ground state with the change in the spin again back. You can see there is a north and south here. Again it will change back the spin while it is entering to the singlet state, and this change in the spin will not happen all of a sudden, rather it takes quite a long time, because there is forbidden spin symmetry, and this does not happen even sequentially, rather it takes a bit of time. And this journey from metastable triplet state back to the singlet state or singlet ground state will result in the emission of the phosphorescence radiation, which is I am now calling as lambda 3. And this lambda 3 is also happening at the longer wavelength region. That is because the electron is losing energy again by intermolecular collision, and then entering to the metastable triplet state. Then it loses a part of energy in the intermolecular collision here, and the remaining energy is emitted as the phosphorescence radiation. So that's why this wavelength lambda 3 is having a longer wavelength when compared to lambda 1 again, because it is happening at the longer wavelength with the lesser energy, whereas the lambda 1 is the shorter wavelength with the higher energy. And as I mentioned, the whole process of this journey from metastable triplet state to the ground state will take up a bit more energy, that is from 10 to the power minus 4 to 10 to the power plus 3 seconds. I mean to say, it is a delay in the fluorescence phenomena. We call it as a delayed fluorescence or phosphorescence. So let me animate this entire process once again so that you guys can take it or pick up this thing once again. So this is the electron that is present in the ground state. It takes up the UV radiation, jumps to the excited state. The spin is still the same in the excited singlet state, but from the journey from the excited singlet state to the triplet state, the spin orientation will change. Keep watching that spin orientation, and we call that process as intersystem crossing. Now the spin orientation has changed, and here in the metastable triplet state, the electron will stay for quite a long time. Because of this forbidden spin symmetry, it won't be allowed to travel back immediately, rather it stays for quite a while here, and then it starts its journey back to the singlet ground state. And during this journey from triplet state to the singlet ground state, there is the radiation that is emerging out, that is we call as a phosphorescence, and this phosphorescence usually is of longer wavelength when compared to the UV visible radiation which was taken up for the excitation process. So this whole process, as I mentioned, will take up 10 to the power minus 4 to 10 to the power plus 3 seconds, and because of this additional time what it takes for its stay in the excited triplet state, we call this as a delayed fluorescence and also as phosphorescence. So as I mentioned, the lambda 3 or the wavelength of phosphorescence is always greater or longer than the absorption radiation. So this was about the fluorescence phenomena and the phosphorescence phenomena. With this, in this particular episode, we have covered the introduction, definition and theory. In the next session, we'll be looking on to the factors that affect the fluorescence, followed by instrumentation and the remaining concept which will be discussed in the subsequent episodes. Thank you very much for your patience and time.